Hello and welcome to this Ambrell Induction Heating Solutions presentation. Now to get the webinar started, here's Brett Daly from Ambrell Induction Heating Solutions.
Thanks, Steve, and welcome everybody to today's webinar on induction heating fundamentals. Dr. Girish Dahaki, Ambrell Senior Vice President of Global Applications, will be presenting today. Girish has over 20 years of induction experience and leads a worldwide team of induction application experts. He holds multiple industry-related patents, has authored numerous papers, and frequently presents at professional conferences on topics such as induction heating, nanoparticle heating, and heat staking. He holds a PhD in mechanical and aerospace engineering from the University of Rochester. Thank you again for joining us today, and now I'm going to turn it over to Dr. Girish Dahaki.
Good afternoon, everyone, and the purpose of today's talk is to basically educate everybody on the fundamentals of induction heating, where it's used, and what the application areas might be interesting to a manufacturer in the manufacturing area. So typically when you think of induction, it is synonymous with industrial heating, because anywhere where you need repeated consistent heat, induction heating is a possible solution for that heating method. So today we are going to basically talk a little bit about what options are available when somebody is looking at induction heating as an alternative to heating. What are the advantages of induction heating? And then we'll talk a little bit about coil designs and other ancillary equipment that an induction heating setup is comprised of. So let me begin. When you think of heat, what's the first thing that comes to your mind? Typically, when we think of heat, we typically picture a caveman sitting in his cave with a fire burning in the front. That's our typical heat, and believe it or not, a lot of the industry even today uses flame for their heating solutions in manufacturing. The advantage of using flame is that it is very easy to set up a flame process. It's inexpensive in terms of the use of flame. However, the environment with a flame type of process is very hot. The temperature control is almost non-existent, and the operator skill that is involved in using flame for manufacturing is very high. We've heard stories where a person who came to us said that when Joe comes in the morning, he is really making good parts because he's on the ball, he's moving the flame around, and he's running parts very well. As the day wears on and Joe is now starting to think whether he put beer in the fridge or he turned his DVR on, the quality suffers. It's actually not Joe's fault. It's any human being would be subject to same kind of distractions. This is where, you need to have a solution that is much more reliable and repeatable. So if an open flame is not a good solution, what might be the next best solution for heating? You could take that flame or use an electric heater and then basically control the heat in an oven or a furnace. This type of heating gives you the accuracy and the repeatability, but it has certain disadvantages of either heating the entire part or you have to run the furnace even if you're not running parts through because of the mass and the size of furnaces. If it's not furnace, what else is available? There is another form of heating that is available that is called as resistance heating. Resistance heating, just because of its name, uses the electrical resistance of the part that you're interested in heating to generate heat. Most common example is the toaster oven that we use every day in the morning when we are toasting our bread. The element that turns orange instantly is heated with resistance heating. This type of heating is very efficient, but it relies on a mechanical contact between the part that is being heated and the source of the electric current. So it's not totally accepted in the industry because of the safety concerns and because of the reliability and the repeatability issues that it has. There is another form of heating that is called as laser heating, which is an upcoming form of heating. Lasers are known to provide a precise location and a precise dissipation of heat in a very small area. Laser heating is upcoming. Lasers are only in a few kilowatt ranges, and the price point for lasers today is much higher than the conventional forms of heating. And then obviously there is induction heating. My goal today is not to convert you to an induction heating expert, but to show you different areas in the industry where induction has been heated successfully and induction is actually providing a better ROI than the other forms of heating that might be available. The biggest advantage of induction heating is that it's highly selective in its heating. Induction heating is able to heat just a section of the part. As you see in your pictures below, on the bottom left, we are heating the extreme or the outside perimeter of a valve assembly. Now, a valve is only being tasked, or the major function of the circumference is where most of the work is being done. So that's the area we want to heat, and we want to affect the mechanical and the material properties of that area. Induction is able to do that. Because we are heating just a small section, as you can see in the picture, the cool down rate is also much faster. And traditionally, cooling is assumed to be free. You take a hot part, leave it outside, and it cools by just natural cooling through the air. But when you're making thousands of parts a day, you have to resort to active cooling, which ends up costing money. So if you're not required to cool a lot of metal, you are going to be efficient in your process by design. Another big advantage of induction is that it is extremely repeatable. Picture on the bottom left is a dental tool which has a plastic handle and a metal tang. And how many times do we sit in the dentist chair and wonder if that metal tang is going to come off the plastic handle? If that thought ever comes to our mind, it would be difficult to sit in that dental chair. So this is the kind of repeatability induction provides. Once the process is set up, it repeats itself consistently and reliably over the lifetime of the product. Induction heating is also able to provide pinpoint temperature control. There are certain industries like the medical industry, like the aerospace industry, where you need positive confirmation that the temperature that you were trying to achieve was achieved. Induction is able to offer that kind of control in a manufacturing process where you could set a temperature and the process will then always go to that temperature without any regard for the starting temperature or any other heat loss that might be happening during the process. The other big advantage of induction is that it's non-contact. When you use flame for heating, for example, there are hot gases that are being pushed onto the part, which is basically heating the part up. With induction, there is no transfer mechanism for the energy to transfer from the induction heating coil to the part. It basically happens through air, but it can happen through vacuum, and it can happen through non-metals as well. So it's a non-contact transfer of energy that does not require a transfer medium. This is really important because the heating element can then be well insulated from the hot part that is being processed. Another big advantage of induction is that it's extremely clean. There are no byproducts produced by the induction heating process. Only products or byproducts might be produced is from the part that is being heated because of the smoke or the fumes that might be coming off the part. Because of its cleanliness, induction finds its use readily in aerospace, medical, fiber optic type applications where cleanliness is of utmost importance. We did briefly touch on this. When you put a part in a furnace, the entire part heats. But what if you only wanted to heat a section of the part? The furnace is only going to be able to heat the entire part. Induction, however, can heat just the section that is of interest. So not only are we efficient in the amount of metal that we have to heat, we are also efficient in the amount of metal that we have to cool. And also, if you're going to introduce a part in the furnace, there is typically going to be a fixture or a holding device that will hold the part in position. When that goes in the furnace, guess what? That part also heats up. So the amount of metal that is being heated is much more if only selective heating is required using induction. Another big advantage of induction that has come about in the last 10-15 years is that the size of induction machines have gone to a very small footprint. Because of this, what has happened is induction heating cells are no longer remote individual cells. Induction can be incorporated right inside your manufacturing cell without having to batch parts and without having to have lots of handling on the parts. Because of the small size and because of the advancements in semiconductors, this is possible. This allows for really efficient manufacturing process. So we talked a lot of advantages of induction. Of where all can it be used? If I started to discuss all the applications that are available with induction, we would probably spend a lot of time here and we wouldn't be able to complete it within the webinar time that is allowed. So I'm going to briefly touch on a few specific applications, but there are numerous applications that induction is used for. And when I say used, it makes money for the people who are using, and it is a good fit for the manufacturing process. So if you think of anything, planes, trains, automobiles, the basic building block for all these devices is metal. Metals are basically the basic building block for all mechanical devices. Obviously, there are plastics that are coming up now because they're gaining in strength and their rigidity and their strength, tensile stresses and everything. But metals are by far still the material of choice when you are considering a manufacturing process. Melting process involves induction. Because we are melting lots of quantities at one time, the induction machines are typically very high in power, but not very high in their frequency. And you might ask, well, what is this word frequency? Just hold that thought and we'll come back to what is frequency. But when metal is melted, we are typically using lots of power to basically melt a huge batch of the metal. Once the metal is melted, then the next process that goes on in the metals industry is forging, which is basically shaping of the metal to make a crankshaft, to make the skin of the car, to make whatever has to be made, nuts, bolts. Their parts are just numerous in their quantity. Forging process again heats the metal. However, in this type of process, you may only be selectively heating the metal. So like in a bolt manufacturing factory, only the section of the metal that has to be formed into the bolt head may be heated. Induction then finds a good niche in that solution. Once parts are manufactured, let's say a crankshaft is manufactured, there are local areas on those shafts that have to be heat treated. which means that they have to wear more slowly. So the metal is heated again. So as you can see where I'm going, the metal is melted lots of times repeatedly to affect the properties of the metal for the particular application. Heat treatment not only happens in automobile parts, it happens in parts that we use day to day. Pliers, hammers, chisels, knives, you name it. And all of these pieces have to be heat treated. They may have gone through one or more of the previous processes that we talked about. So induction heating finds good use in these kinds of processes. And then there are newer industries. The picture on the top right shows the brake rotor of an automobile. Now you spend a lot of money and you really value your automobiles as much as I do, I believe. But whenever you look into the wheel of a car, you see this rusted brake rotor. Well, automotive companies have come up with solutions where they either put a shield or they now coat the brake rotor with an anti-rust coating. Well, this coating typically goes on as a liquid and has to be cured. Temperatures for curing are not high, but if you are making a brake rotor every 14 to 15 seconds, you cannot wait for the paint to dry. Induction heating there finds a use there where we can rapidly heat the metal to basically hasten or fasten the cure of the coatings. The same applies in the bottom pictures where a nylon patch is put on fasteners. This nylon patch basically prevents the fasteners from loosening themselves because of vibration or because of their use in the machines. The next common application for induction is brazing. Brazing is an application where a complex looking part is made by joining two simple looking parts. Brazing is used in steel to carbide type joining applications. It's used in copper to brass type applications. In the plumbing industry, all the plumbing that comes into our houses, all the industrial plumbing that's done, a lot of times uses brazing as a joining method. If it's not brazing, the fasteners or the plumbing devices, there could be brackets on mechanical devices that are brazed. The big property or the big advantage of brazing is that the finished part is stronger, if not as strong as the parent metal. So there is nothing to lose but everything to gain, where you can have two simple looking pieces that are joined together with an additive or an addition of a third compound, and the finished part is as strong, if not stronger, than the parent metal. Soldering is another common application for induction. In a soldering process, the process is very similar to brazing. However, the temperatures of soldering are much lower than that of brazing. Soldering is used in circuit board assembly. Soldering is used in assembly of cables for battery lugs. There are just a million different uses for soldering. Even home plumbing uses lead tin solder to make connections on copper tubes. Soldering is also used in speakers, in sensors of various kinds. So there's just the industry for soldering is also relatively large. And all of this requires selective heating. That's the common theme. Now you're not really heating the entire part. You just want to affect the property or flow the solder in just a localized section of the part. This is where soldering gets used or induction gets used all the time. Another important application for induction is shrink fitting. where a piece of metal is heated to expand the metal so that a cooler piece of metal can then be inserted into that expanded metal. And when the metal cools down, the entire assembly becomes one assembly. This is a very common application in automobile industry, in aerospace industry, because it reduces the number of fasteners that are required. It reduces the requirement for keyways and other devices that have to be put in. So overall, the process is more efficient and it provides a very true finished part. Shrink fitting is used in railroad wheels of all the places. Railroads are carrying goods, and the weight of the railroad or the rails or the rail cars is very important. So most of the railroad wheels are made out of aluminum. However, aluminum is not strong enough to rub against the rails. So just the rims of the railroad wheels are made out of steel. Everything else is either made out of aluminum or some other lighter metal. This allows for reduction in weight and increase in efficiency in rail transfer. There are some unique applications for induction, like all the aluminum foil seals that we break when we get into medicine bottles, juice boxes, toothpaste tubes, Pringles cans, or any device that has an aluminum foil seal that is ruptured before the material can be used. Induction finds its use because it can readily heat the aluminum, and the aluminum can be locally heated only where the seal has to be made. So next time you pick up a juice box, I would challenge you to see or check how many places induction has been used to make the seals. Induction is used in turbine blade heating, where localized sections of the turbine blade are heated to either repair or to enhance the properties of that turbine blade. Induction is also used in the semiconductor industry, where graphite susceptors can be heated with induction with utmost temperature uniformity so that high-end semiconductor devices can then be made on the graphite susceptors. This kind of heating is used in all the chips, all the devices that we use today, from cell phones to computers to televisions. All of them rely heavily on semiconductors. And then there are odd-shaped parts that also get induction heated lots of times. It's a lot of times impractical to have rigid induction heating coils for odd-shaped heating. So there are flexible induction heating coils that are available nowadays for certain sections or certain heating processes where temperatures are either not too high or where the ease of use of a flexible coil far outweighs a rigid coil being used. Like I said, when metals are used for everything, a plastic industry is growing in parallel, and plastics are finding more and more use in all or most of the devices that are being manufactured today. Plastics are stronger, they are glass filled, but they're lightweight. So a lot of plastic pieces are now being made to fit inside cars, inside ships, inside planes. Quick tidbit was that when Titanic sank, there was not one plastic part on that whole ship. It was either wood or ivory or metal. And if you can imagine a modern day ship liner, I cannot imagine whether it would be possible to make it today without the use of plastics. Induction is also used in applications such as annealing of shell casings. Shell casings have to be formed, and local sections have to be heated to get the forming of these shell casings just right. Induction is used in the manufacture of chains. You know, we've all heard the saying that a chain is only as strong as the weakest link. Well, if every link was manufactured to the same stringent repeatability and reliability, then the chain strength would not be compromised. And induction is used to heat the chain when heat treating is performed on the chains. Induction is used in candy manufacturing. Chocolates, the cookies inside chocolates are all made with induction heating because of the speed, reliability, and the cleanliness of the process. There are some atypical applications for induction, like the picture here shows burn-off of enamel of a magnet wire in motors, in rotors, and in a lot of electrical devices. The magnet wire has a varnish coat on it that can easily be heated and removed by the use of induction. We started with the atypical applications with a picture of a railroad. Well, in the manufacturing of rails, when two rails are joined, a lot of times the end sections are preheated before the joint is completed to make endless rails. Induction heating is also used in heating of liners for automobile engine blocks. Liners are typically steel inserts that are heated, and then aluminum is injection molded around these steel inserts so the piston can ride in the steel inserts, and the aluminum just basically acts as the whole engine assembly. Talked about metal to plastic. When you have plastic parts, it's difficult to anchor a plastic part to a piece of metal. So a lot of times a metal piece is heated, and then the heat basically melts the plastic locally around the metal to form a joint. Induction is used in rivet manufacturing. Rivets have localized crumple zones where they fail when put into action. Induction is able to locally heat that section to perform that heating. So we've talked a lot about where induction is used. Let's talk about what is induction. A typical induction setup is shown on your screen here. We're going from left to right. We have the AC line and water being fed to an induction power supply. The induction power supply takes the AC line signal and converts it into a high frequency voltage signal. This signal is then fed into the tank circuit. The tank circuit then feeds the energy into an induction heating coil. The tank circuit, the name implies a tank, which means that it acts as a storage device. So the power supply basically charges up the tank, and the tank is then discharged into the induction heating coil. The part that we are interested in heating, along with the piece in blue that is the temperature measuring device, are the next components in an induction heating setup. And going from left to right, you can see in a manufacturing process where typical sources of variation may arise in a manufacturing process. So let's talk a little bit about the theory of induction. I have to admit that I did not invent it. I'm only the messenger here. So the induction heating basic principle is eddy current heating. And what this means is that if you have a conductor that is carrying an alternating current, as shown in the diagram on the bottom left, it creates a magnetic field around that conductor because of the alternating current in the conductor. Now, if you place another conductor in the vicinity of that primary conductor, it creates a current in itself because of its interaction with the magnetic field. Induction heating basically takes that primary conductor and winds it into a coil. The magnetic field lines are given by the right-hand rule, and if you were to follow the right-hand rule around this copper coil, you will see that all the lines of magnetic field inside the coil are all going in one direction. This is extremely important when a metal part is put inside the induction heating coil. The metal part then interacts with all these magnetic field lines and creates a current in itself. This is what is called as the eddy current. This eddy current is also alternating. However, the heat that is produced is a function of the square of the current and does not really care about the alternating current. The amount of heat that is produced is different for different metals though. Metals like silver, copper have very low electrical resistivity. So the amount of heat that is produced in copper and silver is lower than if you were to look at resistivity of steel, for example. Steel has much higher electrical resistivity. So when put in the same coil with the same parameters, steel part would heat a lot more than a copper or an aluminum or a silver part. We did briefly touch on frequency. Let's talk a little bit about what is frequency. The line current that comes into our houses and into our factories is typically 50 Hertz, which means that the signal changes from positive to negative back again to positive 50 times a second. Induction heating power supplies typically work in kilohertz frequencies. So typically that frequency is changing 50 to 100,000 times a second. It's similar to rubbing your hands together in winter. The faster you rub, the more heat you produce. This is how frequency affects metal heating with induction. The higher the frequency, typically more heat you produce. So the question might be, why would I not use just the highest frequency available all the time? Because I would produce most of the heat or the most efficient heat all the time. The disadvantage to using the highest frequency available is that the cost of high frequency devices is much more than low frequency devices. So if you can run your application with a nominal frequency which is not very high, you probably don't have to invest so much in the induction heating power supply. So that is why even though higher frequency will produce more heat in the part because of the switching at a faster rate, it is not always the accepted or the chosen method for heating. One big difference between induction heating and flame or resistance heating is that induction heating heats the metal into the thickness of the metal. This is very different from a flame type heating where the heat is only produced from the flame onto the surface of the part. With induction heating, heating occurs into the thickness of the metal. This depth of heating is called as the skin depth or the depth of penetration. And there is an electrical formula that is available to calculate this depth of penetration. It depends on the electrical resistivity, the frequency, and the magnetic permeability of the metal. The depth of penetration can be utilized for making or using it for our advantage in manufacturing setups. Depending on the choice of frequency, you can either choose to heat a metal piece as shown in the bottom video that is playing on your screen, or you could use it where it could act as a support without heating at all by itself. So this is where the knowledge of what frequency is able to do is useful, because we can use the same frequency power supply to heat one piece of metal and not heat another piece of metal because of the material property, the shape, and the size that is chosen. In magnetic materials, you get the eddy current heating that we've been talking about, but you get an additional form of heating that is called as hysteresis heating. Hysteresis heating is movement of the magnetic dipoles because of the alternating magnetic field produced by the induction heating coil. Hysteresis heating allows metals to heat even faster than the normal eddy current heating is able to do. So how does one determine what power one needs to heat their metal part? You need to know what is the mass of the part that is being heated, and typically you need to know mass per unit time because you're looking for a rate. You need to know the specific heat of the individual metal that you're trying to heat, and you need to know the rise in temperature that is required. Once you know these three parameters, you can calculate how much energy needs to be put into the part. You still need to account for what kind of conduction losses, convection losses, or radiation losses that might be happening to basically get an accurate count of all the losses that are going to be present in your manufacturing process. Once you know all of these things, you can then get a good estimate of how much energy is required to get to your part, and that gives you a good indication of what power supply may be required. Radiation loss is quite unique because it is not a big factor when temperatures are below, let's say, 1800 degrees Fahrenheit or 1000 degrees C. But above 1000 degrees C, the radiation losses tend to become much more important. We did a small experiment where we only put insulation on this part, and as we started adding more and more insulation, you can see that the temperature started to rise more and more without providing any additional heat or any additional power from the induction heating source. We could almost double the temperature because the temperature that we were after was much higher. There are a lot of numerical simulations that are available in today's world to basically get a good idea of what to expect before one is using or one decides to use induction. It allows us to know what the core temperatures of a part might be. It allows us to know how the cooling curve of the part will be. However, numerical simulations are still limited to very simple geometries. As soon as the geometry of the part gets complex, numerical simulations have a tough time computing and giving results that are very accurate. Let's talk a little bit about coil designs. If any one of you has had any experience with induction, you will appreciate the fact that induction coil designs look like a $20 piece of copper that is wound around a wooden mandrel. However, there is a lot of science and a lot of art behind the manufacturing of an induction heating coil. As you see, induction heating coil comes in different shapes and sizes. Induction heating also is made with different types of tubes. You can have round tube, you can have rectangular tube to make the same induction heating coil. And everything has an advantage or a disadvantage. So when we are worried about efficient heating, we are looking at all these parameters in the choice of not only the type of copper tube that is used, the shape, but also the number of turns that are put on the copper, the shape of the entire copper coil. And as you see in this picture, one piece of coil with the same number of turns, 8 turns, can be chosen or designed to give different heat patterns. You could have one localized pattern in the center, you could have two distinct patterns, you could have just generalized heating, the same type of coil. So that's the science behind and the art behind making the induction heating coils. Once the copper is wound, this copper can then be into multiples of shapes. Like here you can see a 12-position induction heating coil. And the coil is actually on an arc because there is a robot that actually places the parts in the coil, and the reach of the robot is much easier if the coils are placed in an arc. So we design all that based on the manufacturing requirements, and this allows the operator or the company to produce parts effectively and without loss in manufacturing speed. Induction coils, once they are designed, can be encapsulated in ceramics. A ceramic protects the heat from the part from being lost, and it also gives longevity to the induction heating coils, because if the part were to accidentally rub against the ceramic, it can damage the ceramic but protects the copper coil, which is much softer and much more expensive to design. Induction heating coils can heat from the inside of a part as well, as shown in the bottom picture, where you can have a coil that heats on the inside and the outside. Induction heating coils can heat multiple parts at one time, as we just talked. You can have multiple parts all being heated at the same time, as shown in the picture on the right or the bottom. Some induction coils are U-shaped in their design. So these types of coils can basically come in without having to go around the part. So let's talk a little bit about equipment cooling. We spent a lot of time talking about heating. Why would we want to talk about cooling? Well, all induction heating coils have coolant, which is water in most of the cases flowing through them. The water flow is basically keeping the copper of the induction heating coil at room temperature. This prevents the copper from heating. This prevents the copper from burning up. Because we run very high currents through the copper coil, and copper is a good conductor of heat and electricity, the water maintains the coil at room temperature and gives us the repeatability and reliability that has become synonymous with induction heating. There are three different cooling systems that are available to a manufacturing engineer in today's manufacturing environment. The one on the top left is a closed-loop water-to-air, which is nothing more than a radiator with a water tank and a fan. These types of coolers can cool the water only to a certain temperature. Typically, they are limited to 10 degrees above the ambient temperature. So if the ambient temperature is pretty high, the water temperature that it can cool to is even higher. So not a very repeatable or a reliable, because as the ambient temperature in the factory changes, the water temperature is going to change. The next is a water-to-water type heat exchanger, which is in the center of the screen here. This type of cooler is probably the most efficient and gives us the most cooling per square inch of the exchange surface. This type of cooler typically uses a heat exchanger, which is a plate type heat exchanger, to cool a clean process loop from the overhead tank water or some other form of water loop that is not as clean. And then the third one is the closed loop chiller on the extreme right. This is by far the Cadillac of the industry, where it houses a refrigeration unit inside as well as a water tank and does not need to exchange any water from the outside, but can maintain the temperature because of the refrigeration unit and give us repeatable and reliable water temperature. Let's spend a little bit on temperature measurement as well. Temperature is also a big variable when we are considering heating. It's by far the most important variable because the worst call that a manufacturing engineer can get is that it was working well yesterday, it's not working well today. Well, induction heating is very repeatable in the output that it produces. However, there are still different temperature measuring equipment that is available to get better confirmation of the temperature that is being achieved. And last but not least, there are softwares that are available for use for today's manufacturing engineers where we can use this software to track the induction heating process and to record the induction heating process so that we can then accurately and correctly present to our customers that the machines were running flawlessly and they were producing repeatable and reliable product all day long. So this type of software gives a visual picture of an entire production run, for example, or production run over months of continuous run. So with this slide, I would like to conclude my webinar. Thank you very much for attending, and I will open myself for questions.
Yes, thank you very much, Girish, for that informative presentation on induction heating fundamentals. All right, now we're going to kick it off. The first one is, can you explain the difference between flame heating and induction heating?
So typically, flame type of heating is a surface phenomena. All the heat that a flame can impart can only enter the part through the surface. With induction heating, we not only heat the outside surface of the part, but we heat into the depth of the metal. So my favorite analogy is when we are cooking turkeys come Thanksgiving time. You have to have the turkey in the oven for a certain number of hours based on the pounds of turkey that is there. So when you have time-based processes, you have to rely on the thermal conduction. But imagine if you could not only heat from the outside, but also heat into the thickness of the flesh, you would be able to cook the turkey faster. That's how induction heating works. It heats not only on the surface of the metal, but it heats into the thickness of the metal. So for processes where we need good heating to the core of the metal, induction with the right choice of frequencies can provide the heat much more efficiently and much more quickly than a flame type of process.
All right, thank you, Girish. Our next question is, what is the best way to determine if a brazed joint is good?
This is a very good question, and it's a very involved question because first and foremost, you have to determine if the brazed joint is a structural joint or if the brazed joint is a leak-proof joint. If the brazed joint is a structural joint, obviously then the tests that need to be conducted on that are going to be more mechanical in nature, where you'd have to make test coupons and then basically pull the parts apart to make sure that it's meeting the strength requirements from the entire assembly. If it's a leak joint, it's a little simpler. You have to just pressurize the joint that is made and then be able to make sure that the joint is not leaking. So depending on what the end product is and what the end use is how we typically would test the brazed joint.
All right, great, thank you. Our next question is, describe temperature measuring tools used to confirm induction process temperature.
So typically, there are 3 different temperature measuring devices that are available to an engineer today. The first is visual, which is not good, where you can look at the color of the part, and depending on the temperature, human eye is able to detect within 50 to 75 degrees accuracy on the part temperature. We don't recommend this for a manufacturing process though. But I have walked into factories where Joe or Frank would tell me, oh yeah, that part is about the temperature we are used to getting. And that's about 1300 degrees or 1400 degrees, which is very good for that process if it can tolerate it. But it's not a quantitative measure of the temperature. A thermocouple, which is attached to the part, is by far the cheapest and the most accurate way to measure the temperature. However, in a lot of manufacturing processes, it is not practical to attach a thermocouple to every part that is being processed. So even though the thermocouples give you an accurate reading, you cannot basically rely on that being as a solution in high-speed manufacturing. The third and the most common is an infrared or an optical pyrometer to measure temperature. This kind of device basically looks at the radiation coming off the part and converts it to a temperature reading. And the obvious question that might follow is, well, if it's not as accurate, how can we trust it? Well, you can characterize the optical pyrometer or the infrared pyrometer by doing a test where a thermocouple specimen can measure the temperature, and you can make sure the optical pyrometer is reading the same temperature. Once it's calibrated to your part finish and the part shininess and the part characteristics, then you will be assured that every part you make that is being read with that optical pyrometer is going to give you a good temperature reading.
All right, great. Thank you. And the next question is, we have a legacy induction heating system from the 1960s. We have used antifreeze with water for cooling. Is there any reason to add the antifreeze?
This is a very good question. So typically, antifreezes are used in cooling circuits if the cooling circuit is going to be subjected to freezing temperatures. If you have the risk of freezing, the antifreeze will typically lower the freeze point temperature of the liquid and not allow the liquid to freeze. Because when liquids freeze, they expand and they burst all the tubing that they are being held in. So if your machine does not experience any freezing environments, then the antifreeze does not serve any good purpose. In fact, adding antifreeze to water actually reduces the cooling capacity of the water. So that's why we typically would recommend plain distilled water as your choice number one. However, if that water is going to be subjected to a freezing climate, then you can add 7 to 10% of antifreeze to that water so that it doesn't freeze and burst the copper lines. Thank you.
All right, great. And the next question we have here is, would it be possible to develop a system that could travel along the interior of a pipe to heat the inside?
So the short answer is yes. The long answer would be that there would have to be an umbilical cord that would have to be the same length as your path of traverse or the length of traverse inside the induction heating pipe. And it will also depend on what diameter the ID of the pipe is. So given all these parameters, our engineers are able to then accurately determine and guide if this is the correct solution for your heating process. Because one of the biggest things that is done incorrectly in the heating industry is inappropriate or misguided guidance in the very beginning, because everybody wants to sell. However, it is very important to make sure that that does not basically take away from making sure that the process is a good fit for induction. This is what I believe our biggest and toughest job is, to make sure first that it is a good fit, and then look into whether induction can be used through a manufacturer.
All right, and our next question here, we touched upon this topic a bit earlier, so it just kind of builds upon it, and that is in regards to temperature measurement of an enclosed induction heating process, would an optical pyrometer be more accurate than, say, a physical contacting method such as a thermocouple?
So a thermocouple is by far the more accurate of the two. However, a thermocouple has to be attached with either a well joint or by a fastener to the metal part that is being heated, which may not always be practical. However, if your process can tolerate a thermocouple type connection, then the thermocouple type connection is cheaper as well as more accurate in the temperature measurement.
All right. The next question is, does induction heating also induce ground currents into the chassis of nearby equipment?
Great question. And the answer, unfortunately, is yes. Because induction heating coils are just glorified antennas that are creating a magnetic field that is basically being radiated out in the environment. So if a chassis or other metal pieces are within the reach of this magnetic field, these chassis or devices can have some electrical current in them, which is most evident at hinge points or at connection points where the current is forced to go through a small area and you get hot spots. So if you have that problem, there are tricks of the trade that are available to reduce the stray magnetic field, to reduce the heating to structures and devices around.
All right, and we've got another question here, which is, in our process, infrared pyrometers don't seem to be fast enough to return reliable results. Do you know how to make faster measurements on moving parts?
Very good questions. So we have seen this kind of a process when typically fasteners are being made. Like in that fastener type example, we actually started to look at not one fastener for its temperature, but looking at 3 or 4 fasteners at one time by skewing the angle of our sight, so that we caught more than one part at one time. And as these fasteners were moving on, then we could record the temperature and gauge the accuracy of the process. If you need individual part heating or individual part temperature, that is going to be difficult if your parts are moving this fast. What we would recommend in those types of cases is that you would have to resort to some kind of a temperature camera, thermal camera, where then the parts can be tracked as they are moving through, like a computer screen, and then you'd be able to tell if the part was outside of your temperature specification.
All right, great. And I think we're up against the hour mark here, so we're going to wrap up. So thank you very much, Girish, for the presentation and the Q&A. And if anyone has any questions arise, certainly feel free to reach out to us, and Girish will be able to answer the question. We'll circle back to you. And to learn more about how induction can enhance your process and how Ambrell Corporation can help you achieve the results you need for your applications, please visit our website at www.ambrell.com or just reach out to us and we'd be happy to help. Once again, thank you for joining us, and take care and have a great remainder of your day.
Thank you.